Welcome to today's Explainer. Let's just dive right into an incredible cosmic paradox. When we think of mountains, we almost always picture these massive, towering peaks of rock scraping the sky. But what if I told you that some of the most important mountains in the entire universe are barely the height of a pebble? Today, we're exploring a phenomenon that brings together dead stars, unimaginably strong gravity, and tiny, tiny mountains that might just be creating ripples in the very fabric of space-time.
It kind of sounds like a riddle, right? How could the literal smallest mountains in the universe unlock our absolute biggest mysteries? Well, in this explainer, we're going to bridge the gap between the incredibly tiny scale of these physical bumps and the massive, universe-spanning scientific mysteries they might actually help us solve. We're talking about the fundamental nature of gravity, the ultimate limits of matter, and exotic physics that we could never ever hope to replicate in a laboratory here on Earth.
Section 1. The most extreme stars.
All right, so to understand these mountains, we've got to zoom way, way out for a second. Where do these extreme stellar remnants actually come from? Well, when a massive star, we're talking at least 8 times as massive as our Sun, runs out of nuclear fuel, its life ends in a violently explosive supernova. The core that gets left behind just collapses in on itself until it forms what we call a neutron star. And the scale here is absolutely staggering. Just imagine taking roughly 1.5 to 2 times the mass of our entire Sun and cramming the whole shebang into a sphere that is only about 20 kilometers across. That's, roughly the size of a single city. 300 million. To really wrap your head around how extreme this is, just think about that number for a second. Because a neutron star is so immensely compact, its density is basically comparable to the nucleus of an atom. I mean, if you were to take just one single teaspoon of neutron star matter and somehow safely bring it to Earth, it would weigh as much as Mount Everest. That is the equivalent of about 300 million elephants, all squeezed into a tiny little spoon. No way, right? With that kind of mind-bending density comes gravity so intense it is honestly almost impossible to comprehend.
Section 2. Mountains on neutron stars. So, let's travel down to the actual surface of these extreme objects. Given the crushing gravity we just talked about, what does a mountain even look like here? On Earth, obviously, our mountains are kilometers high. They're supported by massive tectonic rock plates pushing against each other. But a neutron star is essentially a perfect sphere. Its gravity is so incredibly strong that it flattens almost everything. Regular matter simply cannot withstand that gravitational pull at the surface. So a mountain on a neutron star, which, by the way, is really just a non-axisymmetric deformation, or a lump, is surprisingly tiny. We are talking about bumps that are a few centimeters, or maybe even just fractions of a millimeter high. But instead of rock, these little guys are supported by extreme elastic strains within the crust, or by unbelievably intense magnetic fields.
This visual perfectly illustrates a truly bizarre contrast. Just picture it. A neutron star mountain, maybe a few kilometers wide, but literally only a few centimeters tall, sitting right next to the massive LIGO observatory. It takes an observatory with arms kilometers long, utilizing humanity's absolute most precise lasers, just to listen for the faint cosmic echoes of a bump the height of a Lego brick sitting on a dead star thousands of light years away. It's just wild.
Section 3. The strongest known crust.
Okay, so you might be wondering, how could a bump possibly survive gravity that flattens absolutely everything else? Well, the answer lies in the crust. The outer layers of a neutron star form this solid, crystal-like crust composed of pressure-ionized atomic nuclei. You can kind of think of this crust as a heroic character constantly fighting back against the crushing weight of gravity. The immense hydrostatic pressure inside the star actually works in its favor by suppressing the formation of fractures or voids. If a microscopic hole even tries to form, the pressure instantly heals it. Because of this redundant, tightly packed structure, this crust is actually the strongest material known to us. It's calculated to be 10 billion times stronger than steel. It has an extreme breaking strain of around 10%, meaning it can be bent and deformed a whole lot before it actually fails, and that is exactly what allows it to hold up those centimeter-high mountains.
So how do these mountains even form in the first place? Well, in binary systems, matter is first siphoned off a companion star. This highly conductive plasma then gets caught in the neutron star's intense magnetic field, and keep in mind, a field that can be a billion times stronger than Earth's. It's channeled along the magnetic field lines until it essentially just piles up right at the magnetic poles. The magnetic force actually confines this accreted material, holding it securely in place against the flattening force of gravity. And boom, you've got a magnetically confined mountain. But these non-axisymmetric mountains aren't just surface phenomena. There are some super complex internal conditions at play here too. Models show that accreting matter can actually bury strong multipole magnetic fields deep down inside. These buried fields then sustain hidden, really intense toroidal magnetic fields near the surface. So it's actually this complex interplay of extreme elastic strain and hidden magnetic fields that holds the mountain's shape, all without shattering that ultra-strong crust we just talked about.
Section 4. Ripples in Spacetime.
All right, let's zoom back out to the macro scale for a minute. What happens when a neutron star, featuring one of these tiny, unyielding mountains, starts spinning at incredible speeds? The absolutely crucial concept here is this. If a perfectly round sphere spins in space, it can spin as fast as it wants, and it won't emit any gravitational waves. None. But add a mass asymmetry, like our little centimeter-high mountain, combined with a rapid rotation, and you get something amazing: continuous gravitational waves.
Let's break that down a bit. Some of these neutron stars, specifically pulsars, can spin over 700 times per second. Literally try to imagine a city-sized object heavier than the sun rotating that fast. As it spins, that little mountain acts as a mass quadrupole, creating a rotating asymmetry that actively churns the fabric of space-time itself. This emits a persistent cosmic hum of gravitational waves. Unlike the really short, violent bursts of waves we detect from colliding black holes, this is a continuous, steady tone. And because these waves carry away angular momentum and energy, they actually act as a brake, causing a gradual spin down, which gently slows the star's rotation over thousands of years.
Section 5. The Hunt on Earth.
Which brings our journey right back to our home planet. How are we actually trying to hear this cosmic hum? Today, giant interferometers like LIGO in the United States, Virgo in Europe, and Kagra in Japan are continuously monitoring the sky, basically listening for this incredibly faint, constant hum. And let me tell you, it is an astonishingly difficult search. Not only is the signal incredibly weak, but because the Earth is constantly rotating on its axis and orbiting around the Sun, the frequency of the signal we receive is constantly changing due to the Doppler shift. Our detectors literally have to perform massive computational gymnastics just to try and untangle a potential signal from the background noise.
So, why go through all this trouble for a tiny bump on a dead star? Well, it's because of what it represents. Detecting these continuous waves is quite literally our only window into the absolute extremes of physics. I mean, if we can measure the size of the mountain and the strain of the crust through these waves, it helps us unlock the star's equation of state, which are the exact rules governing how matter behaves under such crushing pressure. It could tell us for sure if the core is made of exotic particles like hyperons or meson condensates, or even if matter breaks down entirely into a liquid-like state of deconfined quark matter. These are states of matter that are just impossible to replicate in any terrestrial lab.
The ultimate, absolutely thrilling goal of this research can be summed up perfectly like this. Continuous gravitational waves will peer through that window into the hidden depths of neutron stars and the most extreme states of matter. We aren't just looking at stars anymore, guys. We are using the universe itself as a giant particle physics experiment.
And that leaves us with a pretty profound question to ponder as we wrap up this explainer. As our gravitational wave detectors become more and more sensitive in the coming years, what are we going to find? What hidden particles, exotic quark matter, or entirely new laws of physics will these tiny, centimeter-high mountains reveal tomorrow? It really just goes to show that sometimes you've got to look at the smallest bumps to understand the grandest workings of the cosmos. Thanks for joining me today, and hey, keep your eyes and ears on the stars.